for product-free subsets in groups. And this is some so Mohammed here on the left-hand side, that you can see my pointer, so standing here poses next to the grave of the big mathematical house, and next to him Fernando, who also will give a talk afternoon. So we discussed, I think, maybe 2 years ago about this problem, and because nobody ever wrote something up, I decided that maybe this talk is a nice occasion to summarize our discussion. And then you will hopefully see that the thing we are doing are very much related to it. I can make advertisement for a problem you might like to work on. To show you some problem.
Sorry, Frank, I don't. Excuse me to interrupt you. There is sometimes a problem with the sound.
Okay.
I don't know if you can change anything, but otherwise we might just try to continue and hope that it's going all right.
Okay, so I could maybe stop the video. Put it on the how.
Okay. I can hear you, but not very well.
Let's see. That's the way around.
But now it's okay. I think we can just try to.
Okay. So usually in Cologne we are using Zoom, and then it always works, at least most of the time. Okay, so let's try to continue. So I want to discuss a problem in combinatorics with you. And the problem is very simply stated as follows. So we are given a group gamma, a finite group with n elements. And now we ask the question is, what is the size of a largest product-free subset A in gamma? So product-free subset, what it is, there is a subset A of gamma, so that whenever you have x and y in A, you don't want to have the product x times y as in A. So now we are writing the group multiplicatively, and so we are looking at product-free subsets inside of the group. Or shorthand notation, we want to have that if we square the set A squared, so all products which we can build from A, intersect this with the set A, then this should be the empty set. Now, that's a very simple stated problem in combinatorics, and it has the applications, especially in additive combinatorics, or better to say multiplicative combinatorics. And there are many open problems around it. Some more notation. So we're interested in the largest product-free subsets. So let's give it a name, the size, namely the name is mu of gamma. And that's the density of the largest product subset of gamma. So it lies between 0 and 1. So we divide the size of A by n just to be able to compare the groups. Okay, so of course, all nice combinatorial problems go back to Erdös, and this problem goes back to Erdös in 65. And for example, he did some progress, made some progress on this problem. And he discussed, for example, the cyclic group, Z mod NZ. And he showed by some middle third construction that the density of a product-free subset is at least a third, or roughly a third. So let's discuss this problem, just in order to understand the original problem a bit better. So how does the middle third construction work? So it gives us a product-free subset inside of the cyclic group. But of course, now it's a cyclic group, and it's better to write it with plus. So we are talking about a sum-free subset in this setting. And yeah, so what do? We take the cyclic group, we take all the elements here on the cycle, and then we take the middle third, A here. Now, if you write it out, you see the middle third starts with n plus 1 divided by 3 rounded down, and it goes on until 2 times n plus 1 divided by 3 rounded down minus 1. So here in the example, n is equal to 70, so A starts from 6 and goes up to 11. And then you check yourself easily that this is a sum-free set. For example, because if you sum 6 with 6, you get 12. So you're just outside of A again. So you take care of the most right point here. And you also take care of the most left point, because 11 plus 11 is 22, and mod 17 is 5. So you land just outside of A again. And you can do the similar thing with all points in the middle, but because you talked about the boundaries already, it is clear that the set A is a sum-free set. And then the size of the set is basically around the third of the entire group here. That's an easy construction, and it should give you kind of a first idea how sum-free or how product-free sets look like. But of course, the problem is much more complicated, especially if you have more complicated groups. And if you discuss, for example, abelian groups, then there is an exact computation known for the density of a sum-free set for finite abelian groups, and that's a result not too old by Green and Rucha from 2005, which gives the exact number for a finite abelian group, and this number lies always between 2.7 and a half. But it's a highly non-trivial statement to find out this number exactly. Okay, then there is a paper by Babai and Sos from 85, who posed the question, and the answer was given by Gowers in 2008. And the question is, what happens for arbitrary finite groups? Not only for abelian groups, but for arbitrary finite groups. And the question was, is there a universal bound C positive so that the density of a product-free subset inside of gamma is always bounded from below by the C? So for abelian groups, this C lies between 2 divided by 7 and a half. And now the question is there a similar C for arbitrary finite groups? And the answer is no, in the paper given by Gowers. And he, for example, proved that the density of a product-free set inside of PSL2Q is upper bounded by O of n to the power 1 divided by 9, minus 1 divided by 9, where n is the size of the group. And if the group size goes to infinity, then of course also the right-hand side goes to 0. And it shows that there is no C, which makes, there's no universal positive C for all arbitrary finite groups. Okay, and this was done by what we now call the Gowers trick. And this Gowers trick became, in the last 10 years, very influential for the study of quasi-random groups and for growth in groups. And in this talk, I want to show you what the Gowers trick is, and I want to show you some aspects of the trick which I guess were not known to Gowers. So there are ways to improve them, and this is what I want to discuss. And now you might ask and say, hold on. This is maybe nice additive combinatorics, but what I really want, because I go to the POEMA workshop, I really want to have POEMA here. Polynomial optimization, efficiency moments in algebra. And so far, we maybe only talked about algebra because we talked about groups. but all other 4 letters are not. Were not addressed at all before. Okay, so please don't leave the meeting now, because I want to make an argument that the other 4 letters are also very much addressable by this problem. And here's Gowers' trick in a high-level version, and here's also the argument why I think the problem is related to POEMA. And the Gowers trick is essentially an analog of the Hoffman bound for the independence number of a graph. So suppose you have a graph, an R-regular graph with vertices V and edges E. Then the independence number of the graph, so the size of the largest independent set, so a set which doesn't contain an edge, is bounded by the following equation. We take the independence number, alpha, divided by the number of the vertices in the graph. So it becomes also a density, independence density, lying between 0 and 1. And then this is upper bounded by minus lambda min divided by r minus lambda min, where lambda min is the smallest eigenvalue of the adjacency matrix of the graph. And this is negative, so indeed it's really an interesting upper bound here. Okay, so that's the Hoffman bound for the independence number. And Gowers' trick is in a sense an analog of Hoffman's bound, but for a different object, namely for what we will see bi-independent sets of bipartite Cayley graphs on gamma. Okay, and now I want to show you, or the goal of the entire talk is to show you that you can optimize Gowers' trick. So my interpretation or my hope is that the Gowers trick can be potentially be improved by using E and O from POEMA by efficiency and optimization. And the argument is that you can improve Hoffman's bound, and you can improve Hoffman's bound sometimes really drastically by using semidefinite programming, namely by using the lower theta number, which does the following. So instead of using the adjacency matrix alone in computing the bound, we can efficiently optimize over all matrices which have the same support as A, and we can use this, or we can do this by using semidefinite programming. So instead of using only lambda min, the smallest eigenvalue of the adjacency matrix, we now optimize over all adjacency matrices having the same support as A. And for doing this, we use optimization, semidefinite programming. And semidefinite programming in this setting, you can solve efficiently in polynomial time if you want. Okay. So we addressed O and E of POEMA, and now I want to make some advertisement for an open problem, and which you hopefully like and also maybe like to work on. Here it's also an open problem by Gowers, and he was discussing not only product-free subsets inside of finite groups, but also inside of compact groups, for example, in SUN. The SUN are all special unitary groups, so all unitary matrices where the determinant of where the determinant is equal to 1. So this is a compact group, and it has a Hahn measure. The Hahn measure is called mu. And now the question is very similar to the Babai-Sos question, but a bit different because the right-hand side is different. And the question is there a C less than 1, strictly less than 1, such that for every measurable product-free set A, we have that the Hahn measure, the density, so Hahn measure normalized to 1, the Hahn measure of A is bounded by C to the n. Yeah, or in other words, are all product-free subsets which are measurable inside of SUN, are they exponentially small? Yeah. Does this density drop exponentially in N? If you apply Gowers' trick, and I will show you in a couple of minutes how it looks like, if you apply Gowers' trick, then you can show that U of A is bounded by essentially n to the power 1 minus 1 divided by a third. So you have polynomial decay, but Gowers wants more, he wants to have the exponential decay. And my hope is that you can optimize Gowers' trick, so you can also try to optimize this bound, and I hope that at the end it's possible to prove the exponential decay. And there will be more algebra involved. So there will be some representation theory and some symmetry reduction involved. So the A of POEMA will be even used a bit more, not only groups, but also representation theory and symmetries. And if you look up at the representation theory of SUN, they are very much linked to Schur polynomials. So the characters of SUN are Schur polynomials, so you also have a P in POEMA. Yeah. So if you go back to POEMA, we have polynomials to Schur polynomials, we have optimization by SDP, we have efficiency by SDP, we have moments because we have polynomials, and we have algebra because we have groups and representation theory. So I hope everybody in the audience would be happy now. But maybe also it's a good point for asking questions or for complaining about the sound. I hope it's better now, I'm not sure.
So Frank, the sound is very good. You might actually try to turn on the camera again, because
okay. Yeah, I think you can only have one, but let's see.
If there are questions, please go ahead.
Yeah, does it make sense to study the upper bounds also of this quantity?
It also makes sense, yeah, of course. And even in easy cases like L to Q, the best known upper bound doesn't match the best known lower bound. So it makes a lot of sense also for constructions.
Thank you.
So there is also a question in the chat by Lucas Slot. I don't know, maybe you want to ask it, or you don't have a microphone. So why do we expect exponentially small product-free sets in the special unitary group?
Yeah, that's difficult to say. I mean, I think the only argument is that all the constructions we have so far produce only exponentially small product-free sets.
So I also have a question about that. Of course, you look at measurable sets because you want to speak about the measure of it. But you could also ask if every product-free subset is contained in a measurable set of small measure, or is there any obvious counterexample in the special unitary group?
No, not that I know of.
Okay.
There is another question in the chat. Sven Polak, before the one that...
Oh, sorry, I did not see that one. Yes. On which graph do you apply the Hoffman bound exactly?
I will present is not exactly the Hoffman bound, but it's of the Hoffman bound. And then I will show you to which graphs we are going to apply for.
Okay, so this will come. Okay.
Okay,
good. I think for a moment I don't see any other question.
Okay, so this was a high-level picture, and let's go to the details. Okay, so the details start by defining some parameters for bipartite graphs. So bipartite graphs are graphs where I can partition the vertex set into two parts, where the edges are only running between these two partitions. The partition I'm going to use is V1. And for this, for the independent set.
I think it's better if. Sorry. Yeah. I think it's better if you disconnect the video again because the sound is getting worse.
Yeah, thank you. Exactly. That's what I want.
The connection in general, his connection.
Yeah, I think it's a problem in the building. Okay. So now without video, so let's look at bi-independent sets. So these are similar to independent sets, but it's a notion geared for bipartite graphs. So what's a bi-independent set? Yeah, it's a pair x1 of x2, where x1 is a subset of the left bipartition V1, and x2 is a subset of the right bipartition V2. And then this pair is called bi-independent if I never have an edge between a vertex in x1 and a vertex in x2. Okay, and then I define two parameters because I want to measure the size of the bipartition. I don't just count the number of vertices, but I take something more complicated, but this is going to be useful later. And the parameter is called h. H of x1 and x2 is a fraction. On top, I multiply the sizes of the vertex sets, canality x1 times canality x2. And on the bottom, I sum these two sizes of the vertex sets. And then I try to optimize. So I try to find with AHJ, I want to find the largest H of a bi-independent set. Yeah, so I want to find bi-independent sets as large as possible, and I measure the size by this H. So for example, here I have the bipartite graph. On the left side, I have 3 vertices. On the right side, I have 2 vertices. And then I take on the left side the top and the bottom vertex to become the set x1. And on the right side, I take the bottom vertex to be x2. And then if I compute the h of this bipartition, of this bi-independent set, I mean, it's bi-independent because you see there's no edge between x1 and x2. And if I compute this h, I get 2 times 1 divided by 2 plus 1, and this is 2 squared. Just to an illustration how this h parameter looks like. Okay, so I have this h parameter, and now I want to produce upper bounds for this h parameter. And that's the following semidefinite bound. So this bound can be computed by a semidefinite program. So we have a bipartite graph G. Then we have a symmetric matrix Z, where rows and columns are indexed by the vertex set of the graph. And I want to have that Zxy is equal to 0 whenever I have no edge between x and y. Yeah, so in other words, the support of the matrix Z is contained in the support of the adjacency matrix of the complement graph G bar. So I have zeros whenever I have no edge, and I have unknowns whenever I have an edge. Okay, so I have this matrix Z. This is going to be the optimization variable of the semidefinite program. And then suppose that the following is true, that the following matrix, lambda times identity plus Z plus this block matrix, which consists out of blocks, 4 blocks, 0, 0 on the diagonal, and minus a half j on the non-diagonal, where j is the all-ones matrix of the corresponding block sizes. So j, the 1j is of size, the J is of size V1 times V2. And then this entire matrix should be positive semi-definite. Whenever I've found such a matrix, whenever I found such a lambda and such a matrix Z, so that this sum matrix is positive semi-definite, then I have an upper bound for H, and this upper bound for H is lambda, the multiple of the identity. Okay, so now I have a tool for upper bounding the H of G using semi-definite programming, optimizing over all lambdas and over all Zs. And this will be very useful for the product-free subset problem later. Maybe you know something related. So there are two papers on a similar problem, on the bi-clique problem of bipartite graphs, one by Hamas, one by Pastechnik. They also develop eigenvalue or semi-definite bounds. So they are similar, but not the same because they have a different normalization of the size of the bi-independent set. Peters in 2003, he proved that the bi-clique problem is NP-hard. So it's also a clear indication that the problem we are dealing with, finding the optimal AG, will also be NP-hard. But as far as I know, we don't have a proof for that. So the bi-clique problem is the complement of the bi-independence problem, but now in the bi-clique problem, we just look at the size of the bi-clique and not at this parameter H. Okay, so that's a bound. And this bound is very simple to prove, so let's do this. Yeah, and if you know the proofs for the lower theta number, that the lower theta number gives an upper bound for the independence number, then this proof will not surprise you at all. So it follows exactly the same line. So suppose you have a bi-independent set, x1, x2, and then we look at the characteristic vector which you can build out of it. So chi is the characteristic vector, it's 0 or 1, and it's 1 at position when you have x lying in either x1 or x2 and 0 other one. And then you take this vector chi, you take the outer product x chi times chi transpose, you normalize it by 1 divided by cardinality of x1 plus cardinality of x2, and then you have a positive semi-definite matrix here, and this you multiply, takes a trace inner product with the matrix of the theorem. You take the trace inner product between outer product k times k transpose, appropriately normalized, with lambda I plus z plus, and then this block matrix. You know, because the PSD cone is self-dual, you know that this inner product is not negative. And then you know also by straightforward computation that if you take the sum out of the inner product, that the first summand is going to be equal to lambda because of the appropriate normalization. And the second summand, inner product between z and the characteristic vector, times characteristic vector transpose is equal to 0 because the supports are disjoint, and then minus the inner product between this block matrix and this one, minus this fraction, and this is just by expectation, or by expection. Okay. And this is exactly the h parameter of h x1, x2. And then you bring this on the other side, and then you see that h of x1, x2 is less or equal than lambda. So very simple. And this gives you, because x1, x2 is an arbitrary bi-independent set, it gives you an upper bound now for the h parameter of D. Okay, so we have an optimization version for getting upper bounds for h of g using efficient semi-definite programming. Now we want to simplify it, and we want to see what the relation to singular values are. So let's assume, and let's make the setting a bit simpler. So let's assume that G is an R-regular graph, the bipartite, of course, and we also want to assume that both sides of the bipartition have the same cardinality, and both sides have size n. Then let the following matrix be the adjacency matrix of G. So it has a block form, like 0m n transpose 0, because it's bipartite. And we look at the singular values of the block matrix M. The first singular value is equal to R, and then the singular values are here in decreasing order, and the smallest one is greater or equal to 0. So these are the singular values of M. If you maybe don't like singular values, you can also talk about the eigenvalues of the entire matrix, and then the eigenvalues of the entire matrix are plus minus the singular values of M. Straightforward computation. Okay, but we have singular values of M. Then we set lambda in the optimization to n divided by R times lambda 2, the second largest singular value. And we set Z to be n divided by R times the adjacency matrix of G. So now we are specializing lambda and Z to these two values. And it will be easily seen that this is a feasible solution of the semi-definite program, because the matrix, which is built out of lambda and Z, lambda times I plus Z plus block matrix involving the J matrix, is positive semi-definite. Yeah, that's easy to see because, I mean, first of all, the lambda I shifts the entire spectrum so that it becomes positive. And maybe I don't want to discuss too much about this. So the thing is that, first of all, that the largest eigenvalue of Z is equal to lambda 1. And the smallest eigenvalue of Z is equal to minus lambda 1. This is R. And now, by this appropriate normalization, you see that the corresponding eigenvector, which is basically the all-one eigenvector, lies in the kernel of this matrix. And then because you choose lambda so big that it's kind of related to lambda 2, you make sure that all the other eigenvalues are non-negative. Okay, nevertheless, so it's easy to see that this matrix here is positive semi-definite. Hence, the theorem we discussed before, shows you an upper bound for h of g, and this upper bound of h of g is lambda, and this is n divided by r lambda 2. Yeah, so we see that the parameter hg is related, of course, to the size of n, the size of the bipartition, to the regularity, and to the second largest singular value of the matrix n, or the second largest eigenvalue of the adjacency matrix of G. Okay, so now let's get a handle on lambda 2. And this is now exactly Gowers' trick, getting a handle on lambda 2. It's so easy that I give the lemma and the proof here. So the lemma is as follows. So suppose we have an R-regular graph, bipartite. The adjacency matrix is as follows: 0m n transpose 0. Then we have the second largest singular value of m. And then this is upper bounded in the following sense, that lambda 2 squared is less or equal than number of edges minus r squared divided by k, where k is a multiplicity of lambda 2. Yeah, so the second largest eigenvalue is upper bounded in terms of the number of edges, the regularity, and the multiplicity of lambda 2. And the proof is very, very simple. So what do? We compute the trace inner product of the adjacency matrix of G with itself. And we do this in two different ways. So we do it in the combinatorial way. We just compute the number of ones which occur here. So it's a 0, 1 matrix. So the trace inner product is just a sum of 0 and 1s. So how many ones do we get? Yeah, we get a 1 for every edge. And we have to multiply it with 2 because we have m and m. So every edge is counted 2 times. So on the one hand side, of course, then we have that this inner product is 2 times a number of edges. Then on the other side, we compute this inner product, the trace inner product, in terms of the spectrum of the matrix. Okay, and this is equal to 2 times the sum of the eigenvalues of the matrix squared, or 2 times sum of the singular values of m squared. Okay, and then we basically plug it together. So we see that now the number of edges is greater or equal than lambda 1 squared plus k times lambda 2 squared. So from this sum, we just throw away all the singular values which are not lambda 1 or lambda 2. Because they are non-negative, we can throw them away. And of course, we divide everything by 2. And then number of edges is greater or equal than lambda 1 squared plus k times lambda 2 squared. Then we know what lambda 1 is. It's r, so we have r squared for the first summand, and then the rest summand stays. And then we shift the summands around and arrive at this inequality. The second largest eigenvalue, or second largest singular value of m squared is less or equal than number of edges minus r squared divided by k. Okay, and this is Gowers' trick. And this will be very useful now for product-free subsets. So we put it together. The statement is as follows. So suppose we have a group, gamma, and suppose the minimal non-trivial irreducible representation has dimension k. So lambda comes with irreducible representations. There's a trivial one, but there are also the non-trivial ones, and the non-trivial ones should have dimension at least k. The trivial one has dimension 1, and we're going to ignore it. And then the maximum size of a product-free set in gamma is O of n divided by k to the power 1 divided by 3, where n is a number of elements in gamma. And that's now a very easy theorem using Gowers' trick and using what we did before. So here's a graph. So first of all, we are going to define a bipartite graph. So this bipartite graph will depend on gamma, and it will depend on the product-free subset. So suppose we have a product-free set in gamma. Then we consider a bipartite Cayley graph with bipartition gamma gamma. So on the left side, we put all the points, all the elements of gamma. On the right side, we also put all the elements of gamma. And then we say that x and y are adjacent whenever there exists an element A inside of the product-free set, so that AX is equal to Y. So here's a part of the bipartite Cayley graph. We have gamma on the left side, gamma on the right side, and then, for example, the neutral identity element of gamma is connected to all elements in A. And the other elements are connected to shifted copies of A. And this graph is made in such a way that bi-independent sets inside of this graph correspond exactly to bi-independent sets. Okay, then, so let's estimate HAA. So HAA, so A is a bi-independent set. So HAA has size canality of A divided by 2. So canality of A times canality of A divided by A plus A. So this is canality of A divided by 2. Then of course, maybe this is not the largest bi-independent set inside of the graph G, but maybe there's larger ones. So this is upper bounded by H of G. And then H of G is upper bounded by what we discussed before, n divided by the regularity of the graph. And the regularity R is the canality of A times the square root of the second largest eigenvalue, the second largest singular value. And this was again upper bounded by the square root of what we had before. Let's go back. This was upper bounded by this one here. So now we throw the R squared away and we just discuss canality of E divided by K. Okay. And the number of edges is simply n times the canality of A, divided by, now it comes the minimal size, or the multiplicity of the second largest eigenvalue, or the second largest singular value. And now the thing is that if you deal with a KD graph, then the eigenspaces of the adjacency matrix of the KD graph are all direct sums of the irreducible representations. The trivial representations corresponds to lambda 1, and all non-trivial irreducible representations correspond to the other eigenvalues. So that means that we can estimate the multiplicity of the second largest singular value by k being the dimension of a non-trivial irreducible representation inside of gamma. And now we have an estimate on the canality of A on the size of the product we set, and this says that if you put everything here on the right sides, we see that the canality of A is upper bounded by O of n divided by k to the power 1 divided by 3. And now if k is very big, you see that this fraction here on the right side can go to 0 with large n. So now we need a group where k is big. And such groups are given, for example, by PSL to Q. So here's a construction. So we have Q for the prime power for defining a finite field with Q elements. Then SL to Q is simply the special linear group of 2 times 2 matrices with coefficients in FQ. PSL to Q is the projective special linear group where we factor out plus minus the identity matrix. Then it's easy to count that the number of elements in PSL to Q is Q times Q squared minus 1 divided by 2. Then it's a classical statement, but not easy by Frobenius, that all the non-trivial representations have rather large dimension, namely dimension greater or equal than Q minus 1 divided by 2, and this is basically n to the power 1 divided by 3. So this says that the density inside of a product we set inside of PSL to Q is upper bounded by O n to the power minus 1 divided by 9. So this shows that this density goes to 0 when n goes to infinity. So this is basically Gowers' original proof with a hint where we can optimize. So the optimization, going back, the optimization can be done through the theorem by choosing an appropriate lambda and appropriate matrix Z. But in Gowers' trick and what's going before that, lambda and Z were chosen only to be multiples of the adjacency matrix. And that's in relation to Hoffmann's bound. The Hoffmann bound is also a special case of the lower theta number. And there, when we compute the Hoffmann bound, then we also use a multiple of the adjacency matrix inside of the lower theta number. So there's potential which is not explored yet. And I hope that I motivated you to look into that. So if you want to see more, here are the references. 2 papers by Gowers, one on the quasi-random groups, where he proves exactly what I discussed. And secondly, a survey from 2017, which is also highly recommended.